Assalamu alaikum. We are having a new topic of discussion. We're going to discuss differential equations with variable coefficients. Till now what we are doing the higher order differential equation with constant coefficient. Now onward we'll discuss the higher order differential equation with variable coefficient. I just taking a special case of second order differential equation. We have get 2 of x d2y by dx square plus a1 of x dy by dx plus a0 of xy equal to f of x. We have no conditions on a0, a1 and a2. It can be having any form of the coefficients. So this is f of x. If f of x is 0, we say this homogeneous differential equation with variable coefficient. If f of x is not equal to 0, we say this is the non-homogeneous differential equation with a variable coefficient. We take a very special case, and the special case is that we control our coefficients, and we say we having here a2, and here we say x square d2y by dx square. And then we take here plus a1, a constant. We get here x dy by dx. And then we are going to take here a0, and y is equal to f of x. Now this differential equation, you can see we're having this differential equation, and here we multiply by x square and second derivative, x to power 1 with the first derivative, and here is 1 multiplied by y. They are very special case. If I have third order differential equation, I will write like this one, a3 x cube d2y by dx cube, plus a2 x square d2y by dx square plus a1 x dy by dx plus a0 y is equal to, I say here g of x instead of f of x, I take g of x. I will tell you why I'm taking g of x. Here, take here g of x. Again, third order, we are having here the equation, third order derivative multiplied by x cube, second derivative multiplied by x square, first order derivative multiplied by x. They are very special case. These equations we call Cauchy Euler equations. Cauchy Euler differential equations or Cauchy Euler equations. This is a special form of the equation that is called Cauchy Euler equation, when the derivative is multiplied by same degree polynomial of x, or not polynomial of x. Here we say always in this equation x is not equal to 0. So this is always there. Also here we can say a2 of x is not equal to 0. When this is 0, then the degree of the polynomial will change. So we will discuss the solution for Cauchy Euler equation, not for the general equation with the variable coefficient. So I change my title here. I'm going to discuss in this one Cauchy Euler equation. Cauchy Euler equation. Again, we having the homogeneous part and we having the non-homogeneous part. I take here second order differential equation. I take here a2 x square d2y by dx square, a1 x dy by dx plus a0y equal to 0 is homogeneous part. I'll discuss the method for solving this homogeneous differential equation. It can be of order 2, it can be of order 3. We can have any order. What is the substitution? Substitution is y is equal to x to power m. As in constant coefficients, substitution was y is equal to e to power mx. This was for the equations which were non-constant coefficient. Here variable coefficient, we have substitution y is equal to x to power m. We want to substitute in our differential equation. We take the derivative of this one. We get here dy by dx is equal to m x to power m minus 1. we lower the degree of the polynomial of this one. Take the second derivative, d2y by dx square is equal to m into m minus 1 x to the power m minus 2. So these will be my substitutions which I can make in my differential equation. I see what's going to happen. We're having a2 x square, and we put the value of d2y by dx square, this m into m minus 1 x to the power m minus 2 plus a1 x m x to the power m minus 1 plus a0 y is here x to the power m, and this is equal to 0. When I multiply this x square with x to the power m minus 2, I get x to the power m. So I get here a2 m square minus m x to the power m plus. I multiply by x, I get here a1 m x to the power m. So I get here a0 x to the power m is equal to 0. I get here the equation in m. So I take x to the power m common. So x to the power m is common. I'll get here a2m square minus a2m plus a1m plus a0 is equal to 0. Now I discussed before that when you're having the homogeneous differential equation, then y equal to 0 is a solution, always exists. We call this one as a trivial solution. But we are not interested in trivial solution, we are interested in non-trivial solution. So we say this value must not be equal to 0. So when you say this x to the power m is not equal to 0 because it can't be a solution of the differential equation, then we can write what's left here is we're having a2 m square plus we take m common. I get here a1 minus a2 m plus a0 equal to 0. So this equation which I got, I call it as characteristic equation. I call this equation as characteristic equation. Now, as we found the characteristic equation in case of the constant coefficient, where the characteristic equation in the case of the variable coefficient. I come to that one. First I make a quick revision of that so that I can clean this board. So I'm having here the equation, a general equation, equation with the variable coefficients. So a2 of x is a variable, a1 of x is a variable function of x. But I put the condition a2 of x is not equal to 0. We write a special case that we are having here the second derivative multiplied by x squared, first derivative multiplied by x, and then without x, and we are having this special form of equation. When I write third order differential equation, the multiplied by x squared, third order derivative, the same, the third order derivative multiplied by x cubed, second derivative multiplied by x squared, first derivative multiplied by x. These equations I call as Cauchy Euler equations, special equations. I will discuss solution of these equations. Now again, as we are having this non-homogeneous equation, there are two parts of the solution, y equal to yc plus yp. To find yc, we take the homogeneous part of the differential equation. We discuss the method how to find it. We make the substitution for this one, y is equal to x to the power m. Then we are having here the second derivative, first derivative. We find here the derivative of this one, first derivative m x to the power minus 1 using power rule. Again using power rule get m minus 1 x to the power minus 2. I substitute this one in my equation. So I'll get here this x to the power minus 2 and x to the power 2 is cancelled, we get x to the power m. X and x to the power minus 1 is cancelled, we get x to the power m. We take x to the power m common, we get a2 m square, a2 m, then we having a1 m and a0. And then we write this one, we get a2 m square plus a1 minus a2 m plus a0. This we call is a characteristic equation, and we will discuss the roots and solution related to that one for this differential equation.